In this video, I'm going to talk about tolerances on engineering drawings. So a tolerance is the total amount by which a dimension can vary. We'll get more into this in a little bit, but every single dimension on a drawing has a tolerance. Now, we need tolerances, one, because nothing can be perfect, no part can be exactly the dimension, and two, so that we can have interchangeable parts. Interchangeable parts are parts that will fit together at assembly 100% of the time. Now, there's two tolerancing methods to achieve this. The first is called worst case tolerancing, where the tolerances are applied in such a way that if all of the parts come in at the edge of their tolerance zone, the assembly will still work. Now, this can get expensive because the more parts you have in an assembly, the tighter all of the tolerances have to get. And hopefully I can show you that in another video. The other technique is known as statistical tolerancing. This technique uses statistics and probability to allow a greater flexibility in applying tolerances. So let me give you an example of what I mean. If we consider these two parts, so a pin with a diameter of 1 inch plus or minus 20 thousandths, and a hole with a diameter of the same, 1 inch plus or minus 20 thousandths. At first glance, you might think, yeah, duh, these parts will fit together. They're both 1 inch, right? Unless there's some dirt in there, they should fit together. Now, they won't fit together all of the time. If the pin comes in at 1.02 and the hole comes in at 0.98, those two parts will not fit together. So this would not pass the worst case tolerancing technique, but it might pass a statistical tolerancing technique, because if we can establish that our lathes usually make pins small and our drill bits usually make holes large, then we could justify having this tolerance method. Now, it probably wouldn't be, the nominals wouldn't be the exact same, but we could get close. Now, the way to make these parts fit 100% of the time, so now we've made the pin smaller, 0.96 plus or minus 20 thousandths. Now, if the pin comes in at its largest size, 0.98, hole comes in at its smallest size, 0.98, they should fit together at worst case tolerancing, okay? So another thing, if you just took that 1 inch and made it plus or minus a tenth of a thousandths, they still might not fit at the worst possible case. You usually have to change the nominals to achieve worst case tolerancing. Now, we've already stumbled upon a really important concept called MMC. MMC stands for maximum material condition. What it is comparing the largest an external feature can be, so our pin right here, to the smallest an internal feature can be, our hole. It's a convenient way of comparing two mating features to see if they're going to fit together. That's really all there is to it, okay? There's something called LMC as well, least material condition. In this case, we're comparing the smallest the pin can be to the largest the hole can be. So MMC would tell us the minimum amount of room between the two features, so the allowance. The LMC would tell us the maximum amount of room between the two features. So think about the play or the wiggle between this pin and this hole. That's known as our clearance. So we've covered a lot so far. Let's move on to what the actual tolerances look like on the drawing. So the first kind of tolerances we'll talk about are single limit tolerances. So this is minimum and maximum, or abbreviated as min and max. What this does is control one side of the tolerance. So an example, commonly tool relief for radii are stated on the drawing as max, right? You don't want that radius to get too big, but you're okay with a square corner. So this part, radius 40 thousandths max, you could get this part with a perfectly square corner. Now, this is helpful to manufacturing because they can just look at the tool they're using and make sure it's not over 40 thousandths, and they're done. If you put 40 thousandths plus or minus 10, now they need to go and measure it most of the time. Sometimes, you can get away with it. Now, the other kind, minimum, is often used for calling out threaded holes. So the way this works is we've got a 1/4 hole, and it's stated that the thread depth is a 1/4 inch, 0.25 minimum. The thread can go to the bottom of the hole, no problem. That's not going to cause any issues. It's difficult for manufacturing to do, but design-wise, it doesn't really matter. It's a good thing. Now, the tap drill is specified as a maximum. So max tap drill. So you could conceivably have a 1/2 inch deep thread, but it couldn't go any further. So these two tolerances kind of limit each other. Again, this is easier to inspect than specifying 1/2 inch plus or minus 10 thousandths, or leaving it to go to a title block tolerance where it might be even tighter than that. Now, with single limit tolerances, geometry needs to limit the other side, the unspecified side of the tolerance. If you put radius 40 thousandths minimum, the radius could take up the whole part. So this is something you got to watch out for if you're putting this on a drawing, and something you need to watch out for if you're making these parts. Sometimes you'll have extra tolerance with these min and max callouts. So the next type of tolerances we'll talk about are limit dimensions. Now, these are really common on older drawings for a specific purpose. The purpose is for fits. So when you have shafts and pins that have specified fits, so you're looking for a really specific sliding fit or running fit or even a locational fit, typically you need tighter tolerances. And it used to be really common to show it this way as a matter of course. Now, that's not quite true. It's still an option, but this kind of tolerancing is less popular, in my opinion, because it's more difficult to do with a CAD system. A CAD system readily does bilateral tolerances, which we'll talk about next. So, simply put, limit dimensions show you the high dimension and the low dimension. The difference between the high limit and the low limit is the tolerance. It's really convenient when you have parts in assembly that fit together, very visual to see largest pin is at the top, smallest hole is at the bottom. So you can directly compare them without having to do any arithmetic. I can visually see that this pin will always fit in this hole. Now, the larger number is always written on the top. It wasn't always that way, but currently that is the standard. Now, I want to note in notes on the drawing, it's written minimum, maximum. Shouldn't come up too often, but that is part of the current standard. So in this one, our tolerance would be 3 thousandths. In this one, our tolerance would be 3 thousandths because the upper and lower limits are given. So next up, let's talk about bilateral tolerances. These are probably the most common tolerances on drawings that have directly tolerance dimensions. Let's take a look. So on the board, I've got the common bilateral tolerances. So the first one is our unilateral tolerance. We've got our nominal dimension of 1.02 plus 0 minus 4. This gives you no tolerance in one direction, a lot of tolerance in the other direction. Next, we have equal or symmetric, as it's known in a lot of CAD programs. We've got our nominal dimension plus or minus one number. So in this case, it's 20 thousandths. It's a little quicker to write. And then we've got our unequal bilateral tolerance. So in this case, I've shown 1.01 plus 10 minus 30. So you have more tolerance in one direction than the other. Now, I want to make a point that all of these tolerances mean the exact same thing at inspection. There's absolutely no difference between inspecting a part 1.02 plus 0 minus 40 than inspecting a part 1.01 plus 10 minus 30. They all mean this in limit dimensions. The tolerance on each of these is 40 thousandths. Now, specific companies might have rules about where you need to report up the chain of command if you're regularly getting close to your tolerance band here. But as far as ASME is concerned, they all mean the exact same thing. The limit is the limit. A part is just as bad if it comes in at 1.201 than if it comes in at 0.9799, okay? Makes no difference. So those are our bilateral tolerances. Next up, let's talk about some terms for fits. Now, I can't go into how to calculate fits in this video, but there's two terms that are helpful. The first one is basic size. Basic size is just a starting point to calculate your fits, whether you're doing an interference fit or a locational fit or a running and sliding fit. Basically, engineering will come down and say, hey, we need a shaft that's 2 inches, right? That's what we need for the stress. So you'll take that number and use that as a basic size to make your calculations. So the hole might be, 2.02, the shaft might be 1.99, whatever it's going to be. Basic size means something different than basic dimension. We'll talk a lot about basic dimensions soon. Basic dimensions locate tolerance zones in GD&T, and we'll talk a lot about that soon. The next term is nominal size. Now, you've heard me use the term nominal. I'm kind of using it wrong, but basically everybody on the planet does. Technically, a nominal size is a designation for a commercial product. So think about something like a 2x4. If you go to Home Depot and measure what's called a 2x4, you'll find out it's really 1.5 inches by 3.5 inches. 2x4 is just what you call it. Another example are threads. So it's something like a pipe thread. If you get a 1/2 inch pipe thread and you go measure it, the outside diameter, it's going to be like 3/4 inch. It's just called that. Now, back in the day with pipe threads, it used to be that one of the diameters would be 1/2 inch. That's not true anymore. You just have names for these, and then you go look it up in a handbook or something to figure out what the actual size is. Next up, I made a whole video about this, and I'll put a card up here. But real quick, the fundamental drafting rules in the ASME standard, they're lettered. So it's A through M or something, I forget. The very first one, fundamental rule A, basically states that every dimension on a drawing has a tolerance. So this doesn't seem quite true. You see on drawings all the time, a lot of dimensions don't have a tolerance. So there's a couple ways this works. What we've been talking about today are directly applied tolerances, where your tolerance is with the dimension. This is one way to do it. Another way that's common on drawings is to default to your title block tolerances. So the tolerance on the drawing might look like, or your dimension on the drawing might look like this. You've got to go to your title block and figure out how many decimal places you have, and sometimes the length of the dimension to figure out what the tolerance is, and then you can just pencil that in for inspection. Another thing you'll see, you might have a basic dimension. Basic dimensions don't go to the title block, okay? So it's not 1 inch plus or minus something. Basic dimensions get their tolerance from the feature control frame associated with the basic dimension. Okay, so they're still toleranced, but not directly. This should not show up in your inspection report, only the feature control frame associated with that dimension should. Another way tolerances show up are in the general notes. There might be a note at the top of the drawing that says, you know, all machine surfaces must have a tolerance of plus or minus 1 thousandths, whatever it is, or surface finish. Any kind of tolerance could be in a general, sometimes a local note. Another thing you'll see with threads. So you see a thread call out. Where's the tolerance, right? It's not here, and tolerances do have threads, or threads do have tolerances. It's actually here, right? That UNC stands for Unified Course. You have to go to the standard for unified threads to find out what the tolerance is for that thread. So the tolerance on the major diameter, minor diameter, pitch cylinder, all of that will be in a printed standard. Normally, you can also look it up in Machinery's handbook, has the tables printed to find these tolerances. The same thing can be said for other code parts, things like sheet metal or even plate steel have their own tolerances in handbooks. So the tolerance is there. Sometimes you just have to go look for it though. The last one are reference dimensions. Now reference dimensions have no tolerance by definition. They're just there for informational purposes and they should not be inspected. So they're not going to have a tolerance associated with them. Reference dimensions are usually just used to save on shop math. So if you have triangles or some stack of dimensions that's going to be difficult to figure out a specific distance, the designer might put a couple of reference dimensions to help out in interpreting the drawing. Now they can be shown with parentheses, which is the current standard and has been the current standard since 1973. In the 1973 ASME Y145, it was optional whether to write REF in capital letters or use the parentheses. So companies still use both. The parentheses are the current standard though. So next up, let's talk about rule number 1. Now I have a whole nother video about this and I'll put a card up in the corner. I'll just briefly go through it now. Rule number 1 states that any dimensioned regular feature of size must have perfect form when at MMC. So what that means for our purposes right here is that this pin at MMC, so 1.00, has to be perfect in form, perfectly straight, no deviations. The same is true for the hole. At 1.00, the smallest the hole can be, it's MMC, it has to be perfectly straight, perfectly formed. This is a convention that allows us to know parts will fit together. It also allows us to check parts with a gauge. So if we wanted to check this pin and make sure that it did not violate rule number 1, we would need a hole that is exactly 1 inch in diameter. If the pin fits through the hole, we know it has not violated rule number 1. Now, where it gets tricky is, as we've talked, you can't make anything perfect. So you have to use what are known as gauge makers tolerances. So when you make that gauge to check this pin, the gauge has its own tolerance, which is usually really, really tight, tenths of thousandths of inches. The gauge maker, the designer, has to decide one of two things. Either the gauge is going to have the tolerance on the inside so that it may reject some good parts, right? So the hole is set to 1 inch, but the tolerance says the hole can be a little smaller. That would reject a couple of good pins. Or the gauge could have the tolerance on the outside of the hole, so the hole could get bigger. That would allow the gauge to accept bad parts some of the time. This is known as optimistic and pessimistic gauging. Now, we can really not worry about that right now. That's really specific to inspection. Gauges are really handy for parts you're going to make a whole bunch of. So, when they make roll pins and pins for assembly, they have gauges that check that. They have robots that can just drop a pin through the gauge, and if it goes through, it's good. If it doesn't, it's bad. Now, the next thing, there is no requirement for perfect form at LMC. So if the pin comes in at 0.98, it's allowed to be bent a little bit. So think about the pin fitting in that gauge. If the pin comes in small, it can be bent and still fit through the gauge just fine. So there's two requirements for this thing, this part. It's got to fit through the gauge, make sure it doesn't violate perfect form, and we have to make sure that it's not smaller than 0.98, which we can do with 2-point measurements. So measure it here, here, here with something like a caliper. Okay? So that's how rule number 1 applies to individual features. Now, it does only apply to individual features. Now that might sound, just like more terminology, but it's very important for the reason I'm going to explain in a second. So, rule number 1 only applies to individual features. Why does that matter? Let's consider an assembly. We've got 2 diameters, so like a birthday cake shape or a wedding cake shape, that needs to fit in the 2 diameters of this hole. And I neglected to do section lines, so I'll do that now. So let's compare the MMCs to each other. If this smaller diameter, we'll call it the pilot, comes in at MMC, is 0.48 inches. And this comes in and it's MMC. It's also 0.48 inches. Those will fit together. It's going to be close, but they'll fit. We'll say the same thing, 0.98, 0.98, they'll fit together. But there's a relationship between the features that has to be toleranced. Normally, on drawings like this without GD&T, angles are controlled by the title block tolerance. So somewhere in the title block, it'll say something like all angles are plus or minus 1 degree, plus or minus half a degree. We'll say plus or minus half a degree, right? What possible difference could that make? Well, if we just consider the angle of this diameter to the angle of this diameter, say it comes in at worst case, they're a half degree off. What kind of effect is that going to have on these parts fitting up? Let's take a look. So I've drawn that one part with the pilot. Say the smaller diameter is 1/2 of a degree off of the larger diameter. And I've established 1 inch here so we can do our trigonometry. So we want to know how much more room that diameter is going to take up because of this. So essentially both of these diameters might not be able to fit. If the first one won't fit, the second one won't fit. Let's take a look at why. So we've got a triangle here. Let me just draw it a little bit bigger. I'll draw it bigger right here. So we've got a half a degree at the small angle. It's 1 inches on the long side, or on the side. And what we want to know is this right here, right? Question mark. That's how much more room that feature is going to take up in relation to this feature. So we can do some quick trig here. From this angle, we're going to go opposite over adjacent. That's going to be our tan function. So tangent of 1/2 degree equals the missing side over 1 inch. That turns out to be 8 thousandths of an inch. Doesn't sound like much, but when you add that to the diameter, now the parts won't fit. Remember before, they were very close. There was 0 clearance between the parts. You add that 8 thousandths in, they will not fit together, right? So this is an example of why the rule number 1 matters. It only applies to individual features, not multiple features. We have to use GD&T to make these parts fit together. Now, we could also say, okay, well, why don't I just take 8 thousandths off of the diameter of one of these? That would work as well. But what I'm trying to get across here is that if you let dimensions go to the title block tolerances, you can have unintended consequences. So it's good to use GD&T so you don't have to deal with this and do all this extra trig to figure out if the parts will fit together, okay? So that's it for this video. Covered tolerances, the way they look on a drawing, some of the theory behind it. I hope you enjoyed it. Please leave a like, subscribe, comment down below.